In the early 2000s, a field team from the Smithsonian Tropical Research Institute began excavating sediment layers in the Cerrejón coal mine of northeastern Colombia. The site dated to the Paleocene, just a few million years after the extinction that ended the age of dinosaurs. At first, the findings seemed unremarkable: scattered vertebrae, weathered and incomplete, resembling those of large crocodilians known from similar deposits. But as more material was collected and carefully compared, a different pattern began to emerge. The structure of the vertebrae, the articulation surfaces, the proportions, the internal architecture, did not match crocodiles. Instead, they aligned with something far less expected: a snake. Not a modern species, but a lineage capable of reaching proportions far beyond anything observed today. This animal would later be named Titanoboa, reached over 43 feet in length, immediately placed it outside the known limits of living snakes. Yet the significance of the discovery was not simply its size. These bones were not evidence of a monster. They were evidence of conditions. They revealed a world in which temperature, energy, and ecological structure allowed a body plan we consider constrained to expand beyond its assumed limits. Around 66 million years ago, Earth passed through one of the most abrupt biological transitions in its history, the Cretaceous-Paleogene extinction event. Triggered by a large asteroid impact and compounded by volcanic activity and climate disruption. This event removed roughly 3/4 of all species. On land, it marked the disappearance of non-avian dinosaurs, the dominant large-bodied animals that had shaped ecosystems for over 150 million years. What followed was not an immediate replacement, but a structural reset. For a time, ecosystems operated without their former upper limits. Large terrestrial predators were gone. The regulatory pressures they imposed on prey populations, on body size, on ecological roles were suddenly absent. In their place remained a landscape of reduced competition at the top end of the food web. This did not create opportunity in the intentional sense. Evolution does not anticipate or plan, but it did alter the boundaries within which life could operate. In the early Paleocene, most surviving mammals remained small, rarely exceeding the size of a modern fox. Their physiology, reproductive strategies, and ecological niches had not yet adapted to support larger forms. Reptiles, however, followed a different set of constraints. As ectotherms, their growth and metabolic performance were closely tied to environmental temperature rather than internal regulation. In a world where temperatures were elevated and competition at large body sizes had been removed, those constraints shifted. The system no longer enforced the same upper bounds. Over time, this allowed certain lineages, not only snakes, but also turtles and crocodile relatives, to expand in size beyond what had previously been sustainable. This was not driven by aggression or dominance, but by the absence of limiting factors that had once defined the structure of the ecosystem. What we begin to see in the fossil record is not a sudden rise of new rulers, but a gradual extension of biological possibility. The constraints had not disappeared entirely, but for a time they were significantly relaxed. By the early Paleocene, the structure of ecosystems had changed. But structure alone does not determine scale. Something else was operating in the background, less visible, but far more influential: temperature. Across equatorial regions, where northern South America now lies, average annual temperatures are estimated to have reached approximately 86 to 93 degrees Fahrenheit. This was not a brief fluctuation, but a sustained climatic state. Forests were dense, humidity was high, and thermal energy was consistently available across both land and water. For organisms that regulate their body temperature internally, such conditions can be limiting. But for ectotherms, animals whose physiology depends on external heat, the relationship is fundamentally different. In these systems, metabolism is not fixed. It scales with the environment. Maximum body size in ectotherms is directly proportional to environmental temperature. As temperature increases, biochemical processes accelerate. Muscle performance improves. Digestion becomes more efficient. Growth is no longer constrained by the same internal energy costs that limit warm-blooded animals. Under stable, high-temperature conditions, this creates a biological pathway toward larger body sizes, not through selection for size itself, but through the removal of energetic barriers. This is where the significance of Titanoboa becomes clear. Its size was not an evolutionary objective. There is no evidence that larger individuals were inherently favored in a direct competitive sense. Instead, its lineage encountered a set of environmental conditions that allowed continuous growth to proceed further than usual without the typical physiological penalties. In ectothermic animals, body size is closely tied to external temperature and energy availability. During the Paleocene, tropical regions maintained consistently high temperatures. Under these conditions, metabolic processes such as digestion, muscle performance, and growth operate more efficiently. This does not force organisms to become larger, but it allows growth to continue beyond limits typically imposed in cooler climates. In contrast, within cooler systems, a body of that mass would be unsustainable. Movement would slow, digestion would fail, and energy demands would exceed supply. But in the Paleocene tropics, those limits shifted outward. What we observe in Titanoboa is not an organism pushing against its boundaries, but one expanding within them. It did not evolve toward size, it expanded into it. And in doing so, it reveals a principle that extends far beyond a single species. That the scale of life is not only shaped by biology, but by the amount of energy the environment is able and stable enough to provide. As body size increases, biological function does not simply scale upward, it reorganizes. The rules that govern movement, feeding, and energy use begin to shift, often in ways that reduce flexibility rather than enhance it. In modern constricting snakes, feeding is frequently mischaracterized as bone crushing. In reality, the primary mechanism is circulatory disruption. Once prey is secured, the snake coils around it and applies pressure in pulses synchronized with the prey's breathing. This rapidly restricts blood flow, causing a sharp drop in blood pressure. Within minutes, the heart can no longer maintain circulation, and loss of consciousness follows. Death occurs through systemic failure, not mechanical destruction. Controlled experiments on boas have demonstrated that circulatory collapse can occur in less than 60 seconds, with cardiac output failing before oxygen deprivation becomes critical. This suggests that constriction is not a prolonged suffocation process, but an immediate interruption of vital function. In an animal the size of Titanoboa, this process becomes more efficient through scale alone. A larger body provides greater contact area and more uniform pressure distribution. There is no need for venom, speed over distance, or prolonged struggle. The outcome is determined quickly with minimal variability. The increased diameter of the body would also allow pressure to be applied more evenly across major blood vessels, reducing the need for precise coil placement and making each strike more consistently effective. But feeding is only the first phase. Digestion imposes its own demands. After consuming large prey, modern snakes undergo significant physiological changes. Organs such as the stomach, liver, and intestines can increase in mass by more than 50%. Blood flow is redirected, enzyme production intensifies, and gastric acidity rises to levels capable of dissolving bone and keratin. This post-feeding metabolic surge, known as specific dynamic action, can elevate metabolic rate by up to 5 to 10 times the resting level. Effectively transforming the snake into a temporary high-energy system dedicated entirely to digestion. In very large individuals, this process can extend over several weeks. During this period, mobility is reduced. The animal becomes vulnerable, not because it is weak, but because its energy is fully committed to internal processing. The body functions less as an active predator and more as a controlled biochemical system. Digestive efficiency is also highly temperature dependent. Even a small drop in ambient temperature can slow enzymatic activity, prolong digestion, and increase the risk of incomplete nutrient absorption, further tying large body size to stable thermal environments. For Titanoboa, these constraints would have been even more pronounced. Large prey items, infrequent feeding, and extended digestive cycles would define its interaction with the environment. Hunting strategy would favor ambush over pursuit, precision over repetition. This likely reduced daily energy expenditure while maximizing intake per feeding event, aligning behavior with the energetic realities of maintaining such a massive ectothermic body. In this context, size does not expand behavioral options, it narrows them. Size simplifies behavior, it reduces the need for complexity. Not by increasing capability in all directions, but by concentrating function into fewer, more decisive actions. By the time Titanoboa occupied these Paleocene wetlands, it was not alone in reaching an unusual scale. The surrounding ecosystem had shifted in parallel, with multiple lineages expanding beyond sizes typical of earlier periods. Among them was Carbonemus, a side-necked turtle with a shell measuring over 5 feet in length. Its skull alone was large enough to suggest a powerful bite, capable of processing hard, resistant prey. Nearby lived Acherontosuchus, a long-snouted crocodiliform reaching several feet in length, adapted to semi-aquatic hunting within the same river systems. Its elongated jaws indicate a feeding strategy likely focused on fish and other aquatic organisms, positioning it as an active predator within this environment. All of these species are known from the Cerrejón Formation in northeastern Colombia, one of the earliest well-preserved tropical rainforest ecosystems in the fossil record. Geological and sedimentary data indicate a lowland floodplain environment with slow-moving rivers, swampy margins, and dense vegetation. Such environments are not only rich in biodiversity, but also capable of sustaining large-bodied organisms due to continuous resource availability. These were not isolated cases. They represent a broader pattern under sustained high temperatures and stable resource availability. Body sizes across multiple taxa increased simultaneously. Herbivores, omnivores, and predators all shifted upward, creating an ecosystem where interactions occurred at a larger physical scale. Paleobotanical evidence from fossilized leaves and pollen shows dense angiosperm-dominated forests with large leaf surface areas adapted to high humidity and rainfall. Elevated atmospheric CO2 levels during the Paleocene likely enhanced photosynthetic efficiency, increasing primary productivity and allowing more energy to enter the food web. This matters because large predators cannot exist in isolation. Their survival depends on the presence of equally substantial prey and on environmental conditions capable of supporting high biomass. In the Cerrejón Formation, plant productivity, water availability, and climate combine to sustain that structure over long periods. Isotopic studies of fossil soils suggest consistently warm and humid conditions with limited seasonal variation, an important factor as ecological stability reduces stress and allows energy flow to remain uninterrupted across the system. What we see here is not a single species exceeding its limits, but an entire system recalibrated around new ones. Giants do not exist alone. They require a scaled environment. What makes the story of giant snakes more compelling is that it does not end in South America. Tens of millions of years after Titanoboa, on a different continent and within a different ecological framework, a similar pattern emerges, suggesting that this was not an isolated outcome, but a repeatable one. In western India, within Eocene-aged formations dating to approximately 47 million years ago, paleontologists uncovered a series of unusually large vertebrae. These remains were later attributed to Vasuki indicus. Based on vertebral dimensions and comparisons with modern and extinct analogs, estimates suggest a body length potentially reaching 36 to 49 feet. While exact proportions remain uncertain, the mass and robustness of the bones indicate a heavily built animal, possibly among the largest snakes ever identified. The fossils were discovered in lignite deposits in Gujarat, a region that during the Eocene was positioned closer to the equator than it is today. Geological evidence indicates a warm, humid environment with coastal plains, slow-moving river systems, and dense vegetation conditions that would have supported a rich and stable food web. Crucially, Vasuki does not belong to the same lineage as Titanoboa. It is part of the Madtsoiidae, an extinct family of snakes that diverged early and followed a distinct evolutionary trajectory. These snakes were distributed across Gondwanan landmasses and persisted for tens of millions of years separate from the ancestry of modern boas and pythons. Fossil records of madtsoids have been found across South America, Africa, Madagascar, and Australia, indicating a wide geographic distribution linked to the breakup of Gondwana. Their vertebral structure suggests a more robust, possibly less flexible body compared to modern constrictors, implying differences in locomotion and hunting strategy. This separation is not a minor detail. It is central to the pattern. It shows that extreme size in snakes did not depend on a single genetic lineage or a unique evolutionary event. Instead, it arose independently under comparable environmental conditions. Different lineages, same environmental permission. Paleoclimate reconstructions indicate that Eocene India experienced consistently high average temperatures, likely between 82 and 90 degrees Fahrenheit, with elevated atmospheric CO2 levels contributing to long-term climatic stability. Such conditions would have enhanced metabolic efficiency in ectothermic organisms, allowing sustained growth beyond typical size limits. In both cases, elevated temperatures, stable climates, and sufficient ecological support allowed body size to expand beyond typical limits. Crucially, these environments were not just warm, but stable over long periods. That stability reduced ecological stress and allowed energy to flow continuously, supporting large predators that depend on predictable conditions. The repeated evolution of giant snakes under similar conditions points to a broader pattern when energy is abundant and ecosystems can support large biomass. Extreme body size can evolve independently in different lineages. By the middle to late Eocene, the conditions that had supported these oversized ectotherms began to change. Global temperatures, which had remained elevated through much of the early Paleogene, entered a gradual but sustained decline. This cooling was not abrupt, but it was persistent, driven by shifts in atmospheric, carbon dioxide ocean circulation, and the long-term reorganization of Earth's climate system. One of the key transitions during this period was the reduction of greenhouse gas concentrations, alongside the early formation of Antarctic ice sheets. Changes in ocean currents began redistributing heat more efficiently, reducing the long-term thermal stability that had characterized earlier Paleogene climates. For large-bodied reptiles, this shift carried immediate physiological consequences. As environmental temperatures decreased, the external energy available to support metabolism also declined. In ectotherms, this relationship is direct. Lower temperatures slow biochemical reactions, reduce digestive efficiency, and limit sustained activity. Enzymatic processes that drive digestion and muscle performance are highly temperature sensitive. Even small decreases in ambient temperature can significantly reduce metabolic throughput, particularly in large organisms where energy demands are already high. For smaller organisms, these changes can be accommodated. Growth rates adjust behavior shifts, and populations persist. But large bodies operate under tighter constraints. They require greater absolute energy input, longer digestion cycles, and more stable thermal conditions. When those conditions begin to fluctuate or diminish, the margin for survival narrows rapidly. Larger ectotherms also face challenges related to heat exchange. Their lower surface area to volume ratio slows both heat gain and heat loss, making it more difficult to recover optimal body temperatures in cooler or more variable environments. Large bodies do not adapt downward easily. Evolution does not simply scale back size in response to environmental stress, especially when that size is tied to a highly specialized ecological role. Instead, populations decline. Reproductive rates fall. Juvenile survival decreases, and over time the lineage contracts. Fossil records across multiple reptile groups show the same pattern. Large species disappear while smaller, more adaptable forms persist, pointing to a broad ecological shift, not isolated extinctions. In the fossil record, this does not appear as gradual reduction. It appears as an absence. Today, global temperatures are rising again, but the context is fundamentally different from the world that once supported giant snakes like Titanoboa. The current phase of warming is rapid unfolding over decades, rather than the long, stable intervals of the Paleocene and Eocene. Atmospheric carbon dioxide is increasing, and in some tropical regions, average temperatures are beginning to approach those estimated for ancient greenhouse climates. At first glance, this might suggest a return to similar biological possibilities, but the system that once sustained those possibilities no longer exists. Modern ecosystems are fragmented. Continuous tropical forests have been reduced, wetlands drained or altered, and river systems disrupted. These changes limit the flow of energy through food webs and reduce the total biomass that an environment can support. At the same time, temperature increases today are unstable, marked by variability extremes and rapid shifts rather than long-term equilibrium. For large ectotherms, consistency matters as much as heat. We are changing temperature, but not rebuilding the system that supported giants. In the end, Titanoboa is best understood not as an exception, but as evidence. It reflects a moment in Earth's history when environmental energy sustained heat, high productivity, and stable ecosystems allowed biological systems to operate at a different scale. Its size was not an exaggeration of life, but a measurement of what that system could support. When those conditions shifted, the outcome was not conflict, but incompatibility. The giants did not fail. They simply no longer fit. If you're interested in how environments shape life across deep time, subscribe to our channel, because the story is rarely about the animal, it's about the system that made it possible.